This is really a talk about two different things. By the way, that image, I basically looked up a image for digital sun, and I wasn't disappointed. I just thought that was just too cool to leave on to not put up there. Okay, this really is two talks. We're going to be talking about the nature of technology revolutions, even if you have no interest in solar sails, and then we're going to be talking about a solar sail concept that is basically takes advantage of these methodologies to make a very advanced, basically to try and cram about 30 years of progress into a very short timeline. And so it should be an interesting little trip as we go along through here. So something I came up with here was what I call SECADs, or Science, Engineering, Convergence, Affordability, Democratization, and Scale. I'm glad I did not, I originally called this Cs and then Seeds and then finally SECADs. I'm just glad I'm not doing this too many more years, or it'll be supercalifragilisticexpialidocious or something silly. But it has a purpose here. So with technology revolutions, invention itself, we have key components in a sort of life cycle. The first is science. What is possible and what already exists in nature? The second is engineering. What can we build that extends what is possible into the physical and technological world? Science and engineering are like the left and right feet by which technology development walks, but that's just the beginning. New concepts are invented, they become available for what is called convergence. Convergence is also a term in evolution, by the way. Technology revolutions are typically several unrelated inventions that are used together in novel ways. Convergence is so powerful, it's often mistaken for the concept of invention itself. Some books actually can use the two terms, but convergence is just an important phase of that. Convergence is a machine which creates a critical mass that ignites mainstream development in a technology. So just as science and engineering work together, affordability puts technology in more people's hands, which in turn drives democratization, and that makes the technologies more mainstream. These cycles drive investment, which drives further innovation. Mature technologies are then scaled in size and power to fit in different niches, therefore the term scale. They can be made larger or smaller as needed. So when we talk about this, I kind of want to clarify what this is in relation to the concept of STEM. STEM is great for education because we're talking about science, technology, engineering, and math. Those are entirely different subjects when you're a student, but it's not technically true because math is technically a hard science. Therefore, it's not really a separate field. And technology is simply an instance of engineering. So when we say 1950s technology, it's like a balance sheet. It's a snapshot of what engineering is at the time, or what is available at the time. So that's why SECADS actually consolidates all four of these terms into just simply science and engineering. So STEM is great for education, but SECADS is great once you graduate. So we mentioned convergence as a powerful engine. Normally, when you talk about something, you talk about exponential or maybe Q scale. And then if something is really exploding, you talk about factorial, where it's one, it's 1 times 2 times 3 times 4 times 5 in this case. Convergence can be even more powerful than that. So let's look at these three inventions. These came around the same time, around 1900 to 1950. We have aircraft radar and voice radio. So out of these three things, we don't have 6, we have 16 major categories of inventions out of 3 building blocks. So this is why this is such a powerful engine. So we're going to get a little bit into history here. We're going to use a case study of the electric motor. The electric motor actually has sort of this almost mythical history going all the way back to Ben Franklin in 1745, when he observed that there was such a thing as electricity in nature. With it's not quite the lightning experiment, but you get the idea. That's a little bit apocryphal, but the observation was there in nature and was actually carried out in France. But anyway, so what I did with this chart is I took this SECAD scale and I assigned 1 for science, 2 for engineering, and so forth all down the line. So in the early days, we have essentially test bench experiments. We have a slow realization after about a half century that something is going on in nature with electricity. Then we start with the very basics of engineering with little workbench models that prove different minor forces that could just barely be detected over about a 35-year period. Then when we make the first practical electric motor, in 1834, we see a sudden jump in technology and affordability. And then for the most of the 1800s, down the line here, is when we have a whole bunch of inventions relative to practical electric motors being used in commercial or industrial scales. And then, of course, in the 20th century, then it became more home scale with power drills and every other little thing. And then right up until the very end, we even see this reluctance motors combines several forces in unique ways. It was just invented very recently in comparison. So when we graph this out, we have one for science, two for engineering, and so forth. What we see is that we see this sort of back and forth spark gap for about 35 years, and then all of a sudden a jump. And then these are still being done, but we have this huge gap here between convergence, affordability, convergence, affordability. As we combine different systems and make them more affordable, we have this whole thing. And then all of the 20th century is right here. So we take this over to, democratization and so forth, the rest of the Secant scale. That there's just not enough room on this graph for that. So we wanted to focus on this initially here. So we end up with a sort of fire break between science and engineering, jumping out of the lab and then becoming a commercial product, and then eventually going on to being a domestic product. So when we look at the history of the solar sail, we have a very similar thing. And again, we're talking about electromagnetic fields and so forth. In 1610, we have this almost mythical thing where they first discovered solar wind because they saw that comet tails were blowing away from the sun. And Kepler came up with the idea that, well, someday maybe they'll make ships that can be blown by that wind. But it wasn't until 1973 that somebody actually did attitude control on Mariner 10 with little tiny solar panels or solar sails at the tips of the solar panels on that vehicle. And then on down the line, we just have one concept with photons, then magnets, then M2P2, which is basically making a bubble and holding a plasma that is injected into that bubble. It's not natural solar wind. It's sort of an artificial sail made of that. And then there's an electric sail proposal out of Finland. And then we finally get two practical designs flown within about a year of each other, really. And then 5 years later, the Planetary Society actually makes the jump over to affordability because that was a private effort, not a public one. It's interesting. And then dipole drive is something that Robert Zubrin proposed a few years ago. They used yet another principle. So I find it interesting that of all these solar sails concepts, two of them were invented by Robert Zubrin. So when we scale this out, we see science, 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 a little bit of engineering, and then boom, this little affordability jump over here. But at no point have we really done anything in the way of convergence. So if we look at this on the same time scale as the electric motor, solar sails are basically the same state of technology development that the electric motor was between the years 1834 and 1864. So, but since nothing has happened in this convergence scale, let's see what we can do about changing that. So we're going to use CCADs here, not simply as a history lesson, but as a methodology. Instead of just following the trail, we're going to be doing something more like building a road. So we're going to work our way down this list here. What is the nature of deep space? How do we build sails? Is there a mixed method of propulsion? We're going to bring in yet another technology of genetic algorithm design. Then we can worry about these sorts of innovations down the road. So what exists in deep space? What is the science? Well, of course, they were originally basically giant mylar sails, but that's only 9 newtons per square kilometer. It's a very weak force. So several concepts about proton driven, in other words, the actual solar wind coming off and not simply the light from the sun. So that's where a lot of things like Zubrin's dipole drive and so forth come in. And then there's field driven, which is the idea of using electrical or magnetic bubbles to propel things. And this is kind of a mixed media because there is an electrical and magnetic forces in play here, which are obviously closely tied and so forth. So engineering, what can we build? Again, laser sails, light sails, solar sails, the dipole drive that Zubrin came up with a couple of years ago, and then which is the idea that you basically have two screens. Basically, think of an electric charge across two, almost like a mosquito screen on your window, and one is charged one way and the other is the other way, and basically it repels it accelerates the electrons through it and repels the protons. And since the electrons are much lighter than the protons, then it provides propulsion. Or maybe I've got that backwards. I may have said it incorrectly. And then field driven is what we talked about here. So there's your science, there's your engineering in isolation. But what about a convergence? Can we take electrical fields and magnetic fields and do something like a Lorentz force, where if you have an electric field going one direction and a magnetic field going the other direction, and you have a working field that working fluid or gas that is electrically charged, it can actually be forced through that through an aperture on the z-axis. This is how magnetohydrodynamic systems work. If you remember the movie Hunt for Red October, the idea there was seawater was able to be propelled in this way. But there are other systems that use plasma or rocket exhaust or so forth. What about using a phased magnetic array? Similar to a phased array antenna, but we're using magnetic fields or something like that. Can we make a sort of gun? Can we make fields that work in 3 dimensions? Essentially an artificial sail that could be vibrated or whatever in the same way that say a jellyfish pushes water out of its way. Could we make a plasma bubble, and instead of just holding onto it and using it as a sail, could we then force it out of a electromagnetic railgun and use that as a reaction mass? There are all kinds of different ideas you can do there if you think in terms of convergence. And then, so what would this concept be? So the reason FlexSail was come up with, because it's a flexible design for a solar sail. It involves a little bit of everything. So the simplest way to do that would be, hypothetically, this is our workbench version, is we take a controller connector that would connect to other vehicles or other pieces of vehicle. We would have a photovoltaic part. We would have an electrically charged part for the dipole drive concept. We would have a reflecting film for the conventional solar sail, and then an electromagnetic array which would have wires and magnets and so forth within it. So the concept there is, okay, what if this is what you've got? How do you proportion them, and what's the best geometry for it? So this is where we get into genetic algorithms. The idea is that you would make a sample version of the vehicle in a digital computer model that would essentially be like a flight, like a wind tunnel, except it's the solar wind that you're modeling in this case. So we would simulate each configuration of these. We would change the proportions of different parts. So the foil is larger, the magnets are larger, or whatever, and we would just run them in comparison. And then we would say some are weaker, some are stronger. We take the stronger ones and we enhance them. We take the weaker ones, we eliminate them, and we run competitions between them, all digitally, all automatically. This race car frame was designed in this manner, where it was digitally tested over and over and over again, thousands of times in simulation. And what they ended up with was something that looked like the inside of a bird's wing. This is not a top-down blueprint. This is the sort of thing that you would do if you were designing something in nature. So it's the same concept here, except done in a computer at very high speed. So in this case, we would change the dimensions, ratios between parts, angles, voltages, particle interactions, all these things could all be worked out in that way. We may get rid of the reflective film entirely and just do everything electromagnetically because it would be a much more powerful system then. But the nice thing about the reflective films is it requires no power. So it may be all photovoltaic. It could be like a dragonfly wing. It could be like, just a simple, spinning disk. It doesn't matter. This is it's up to the computer to figure that out. We would evolve a modular concept. So we start with our modular ribbon. We go to genetic scaling. What's next? Well, what about simulating it based on actual solar wind data from solar weather satellites such as SOHO and so forth out in deep space? We can not just model a simple wind tunnel, but actual weather in space and see how that works, because something that might work just fine in a constant speed environment may actually be much more complicated if there's a flare or whatever, or it may take advantage of those situations. In addition to that, what if these things can be made to interact with each other the same way that a flock of birds are able to use the wings of the bird in front of them to augment their own lift? Can we make fleets of these solar sails that interact with one another? And this would be incredibly powerful at scale. So then we go on. So this is what we normally think of as a solar sail, a single vehicle going somewhere in the solar system, probing the robot, probing the asteroids or whatever, or maybe we could make a solar weather research fleet. But what about having something like this where we have maybe when Elon Musk sends his fleets of vehicles to Mars, we could have a fleet of solar sails that are designed specifically to block electromagnetic storms from solar flares flying upwind of them, that can not only issue warnings to the crew, but also augment their protection by essentially providing a blast shield like an umbrella ahead of the vehicles. Or we could use something on that same scale to do asteroid mining. There's also ideas like Jim Green, who spoke, I believe, this morning, talks about making a big L1 thing between Mars and the sun to block the solar wind from causing so much interaction and stripping away the atmosphere of Mars. Something like that might work, and something like this could actually be station keeping. In a similar manner, we could have something like this. When a solar flare comes into Earth, the equator is pretty well protected, but the poles are wide open. In fact, it actually amplifies the force coming in the pole. So when there's a major Carrigan event type solar storm, it would come in through the poles, dissipate through the Earth's atmosphere and ionosphere, and eventually cause blackouts and possibly damage to electronics. What if we made satellites that, even if they only worked once, if they were like something that was there to fire and then burn out, they could protect the vulnerable areas over the poles, and they could either just be a simple deflection, or they could hold the energy in their own magnetic fields and then go into the Van Allen belt and release it, or they could go clear off to the other side and release it there so that it blows away harmlessly in the solar wind. So there's ways we could protect Earth. With Mars, we could put these things not only up and down, but we could also put one, if it was a shield, it could go towards the sun in the same manner as Jim Green's shield, except much closer and much smaller. And you could have fleets of them. So you don't have to do everything at once. You can do a little bit at a time, 1%, 2%, eventually working your way up. Or you could make something that captures the solar wind, similar to the Earth's magnetic field, and then just turns off when it gets downwind and releases it so that it blows harmlessly beyond Mars and protects Mars that way. So on the one hand, we preserve technological life on Earth, and we are able to bring life to Mars, because according to Jim Green's estimates, if you just block all this wind, there's enough outgassing from Mars that you will actually get enough of an atmosphere to support plant life. So if you would like to collaborate with me, I am not a scientist or an engineer to the degree that I can actually take this much beyond these slides. So if you know anything about physics, the space weather, aerospace engineering, genetic algorithms, or flow simulation, here's my contact info, and we can pick it up from there. So any questions?
Thank you so much, Kent. That was great presentation. Thank you so much for your time. We do have a couple questions, and I'll read them to you. Let's see. There's a question from Bill Lewis, and he wanted to know where the ring image from the beginning. He wanted to know if it was Dr. Strange.
Yeah, I'm looking at the questions now. That kind of cracked me up. I basically just, when in the new version of PowerPoint, if you say, give me an image search off the internet, I just put in digital sun, and that popped up, and I thought it was gorgeous. So I just stuck it up there, and then I took a 3D model of a ship wheel and I threw it over the top of it. So that's all that was.
It was a cool picture. I would have to agree. The next question is from Dusty Green, and he was wondering, like, hypothetically, if you had access to Tesla and SpaceX parts, factories, or workers for just 1 week, what would you be able to build?
Oh, for something like this, actually, the people if I was to build this, it would be the Starlink group. In a perfect world, to really answer your question and not limit it to a week or whatever, I would say get the Starlink group once they're, basically take that hardware and build the prototypes. I would probably get a university program or somebody with genetic algorithms and have them chew through what the design would look like. And then in terms of a physical fleet, I think the ultimate end of this would be, how when they launch the Starlink satellites, there's like 42 of them in the shell, and then they just release them all into space. I would love to see like a bunch of these things being released at once, climbing out of the low Earth orbit with using the Earth's magnetic field for propulsion, and then once they got into deep space, reconfiguring themselves like transformers or some sort of Voltron combination into a large vehicle that could then do more serious work. I think that would be the beautiful approach to that, and that would be precisely the sort of thing that they could do.
Thank you. We're going to go to AltSpace VR. Can you hear me for your question?
I can hear you. The question is, can you hear me?
Yes.
Yes.
Oh, good. Okay. So I want to thank you for putting the information about Jerry and Larry up on your screen about Mote and God's Eye. Jerry's actually my uncle, so I want to let you guys appreciate that. Right. And so I wanted to know the science behind it was actually done by a gentleman named Dan Alderson from JPL. When they put it in the book, how actual do you think that is now? I mean, can we create ones like they described in there, or has science gone so far behind some?
You're cutting out. I'm sorry. I think you were asking, can we do something like in the book?
Yeah.
I'm not sure because it's been a long time, to be honest. So I seem to recall that being set like way in the future, though. So, I couldn't tell you what the scale is. The beauty of this design as I'm putting it together is that it could be any scale. I'm talking about anything from little probes up to planetary defense systems. So generically speaking, I would say so, but I'm way too rusty on my classic science fiction to really tell you. I apologize.
That's okay. Thank you anyway. I appreciate it.
I appreciate you asking. It's an honor to have somebody from that family in VR having to answer me that question. I'm going to tell my kids about that.
That is incredible. Thank you, Kent. I have another question for you. Have you developed models in order to be able to predict affordability, perhaps something in Excel, etc.?
Not really, because it's hard to do are you talking about in general on the technology front or on the solar sail front? That's the question. The solar sail, my original concept was you could do a lot digitally before you ever cut metal. So, atoms cost money, electrons are free is the short answer. So if you can use open source, or if you have, part of the reason I said college students is because they get access to $5,000 CAD programs for basically nothing, or as part of their tuition or whatever. So if I was to say, grab like a graduate, physics class and have them work on some of this, that would essentially be affordable. That's where I would get started with it. But from there, in terms of prototyping, it's really a question of what does the model say how big it is to be practical. My gut tells me it would be at least the size of a Starlink satellite, so like $100,000. But if it was a CubeSat and it could be done for $30,000, that would be obviously a cool thing.
Thank you. That question was from Adil Khan, and he does have an idea that I will read. He said maybe an OpenAI gym instance could be created. For example, in order to make devices for capturing all the debris in LEO and elsewhere.
That's certainly an interesting idea. It's an excellent application to this because you are talking about the problem of capturing debris is you need a bunch of small, affordable things with a ton of delta V that can get into an orbit, find something, grab it, and then bring it down, or harvest it and move it somewhere else, like to a factory or whatever. So if you put that into your artificial intelligence model as the goal, then you make the best hunters you can for the prey or the field of grass, or however you want to put it. of hunting down space debris and going from there. So again, it's a matter of you put it in the model and you see what happens. And if the technology is not adequate, and let's say we did this in 2024, okay, try it again in 2026, because you got to skate to the puck on that. And then if there's something you can drive, where it's like, oh, well, this technology doesn't exist for another 5 years naturally, but we're just going to go and build it, sort of like the iPhone was done. Then you can push that boundary. My goal with this is to take about 35 years of technology advancement and cram it into as little as possible, so like maybe 5 years. I'm kind of reading these along. Protect the IP for CCADs. I think I'm going to probably write a book about it in the next year and push it as a methodology, so that my name is associated with it. And there's a lot more to it than that. In fact, there's a few intentional vagaries in this presentation just to protect the IP. So the principles are there, but it's going to be a little more sophisticated as I dig into it a little deeper. So Adil, I'm seeing you in the chat. Do you have a experience with this? Would you like to collaborate with this in the future? Go ahead and find me on LinkedIn.
I think that was the last message. I just got one more. We have about a minute left. I don't see any other questions. Is there anything else that you would like to add, Kent? You have about a minute left.
Basically, if the CCADS model, and I'm sorry, somebody in the thread asked what it stood for. I'm going to back up a little bit. The idea is, here we go: science, engineering, convergence, affordability, democratization, and scale. If this helps you become your own little, Elon Musk, please go for it. That's part of the reason I'm putting this out there. Yes, I will eventually write a book on this and possibly teach classes, or maybe I'll get some adjunct thing at Singularity University or whatever. Maybe this will take on a life of its own. That's my journey. But whatever this does to help you in your journey to become your own best inventor, please make this happen. That would be the greatest legacy that we could have.
Wonderful, Kent. Thank you so much for your great presentation. I was lucky enough to see his previous one. The track talks will be edited and put on YouTube, hopefully within the first couple of weeks after this conference. If you missed his 3 o'clock Pacific time abstract talk, you can view it on YouTube in just a couple weeks. Thank you again, Kent. I hope you enjoy the rest of our convention, and all of our participants. Thank you again for joining us. Our next session starts right now in this room and 3 other rooms. Thank you so much. I'm going to end the call now.
Thank you.
Thank you.
Take care.